Now that we have covered the definition and some of the arithmetic with complex numbers, we're going to get into how that applies to trigonometry. Okay, and so we're going to look at what we call the trig form or trigonometric form of complex numbers. Some people also call this the polar form of complex numbers. Okay, so how does this relate to trig? Well, a complex number, remember, has two parts, a real part and an imaginary part. Okay, so a complex number can always be written in the form a plus bi, right? I is the imaginary unit, where I is the square root of -1, right? That's the imaginary unit. And then a and b are real numbers. And a, b are real numbers, okay? So that's, those are the definition of a complex number, right? Those are the different features. And so you have what we call the real part, which is the a, and the imaginary part, which is the bi. Okay, and those two things are added together to give you a complex number. Now, it's possible that one of these might be 0, in which case, if the a value is 0, then the bi is all you have, and so imaginary numbers are technically complex numbers. In addition to that, the b could be 0, in which case all you have is the a, and so all real numbers are actually complex numbers too. Okay? So what we do is we can represent complex numbers on a graph just like you can any number. Generally, with a real number, we put it on a number line between -infinity and infinity. Okay? So you have the real number line, okay, the real number line, and any number, any real number can go on that real number line. So the number 2 is over here, the number -5 is in here somewhere, okay? So what we do to plot complex numbers is complex numbers are not found on the real number line. They're nowhere in there. They're not between -infinity or infinity. They're not on this number line. And so we need another number line to give us the imaginary numbers. Okay, so we're going to make that number line perpendicular to the real number line. Okay, it's going to look a lot like the xy axes. It's not very perpendicular, is it? Bad drawing, I suppose. I could probably get that to look a little nicer. Okay, so that's the imaginary numbers. Well, I can't write. Okay, so now we have what looks like an xy set of axes, right? You've got the real number line, or the real axis, we often call this. Looks, it's kind of like what we would have as an x-axis, and the imaginary number line, or the imaginary axis, kind of like the y-axis. And when we plot now a complex number, it's on a plane instead of a line. So we have the real number line. We also have the complex number plane. Plane is just a flat two-dimensional surface. And so if I wanted to plot the number 2 plus 4i, well, that would be 2 in the real direction and 4 in the imaginary direction. So we plot 2, 4, and it would be a point on the plane, kind of the 2, 4 coordinate. So this point is now the number 2 plus 4i. Okay, so that point represents the number 2 plus 4i. Okay, and of course we can do that with any number, all right, any complex number. We can do that with real numbers as well, right? The real number 1 is right there. It's 1 plus 0i. The imaginary number 3i is on there, right? It's 0 plus 3i. And so any real number, any imaginary number, and any complex number can all be plotted on this plane using essentially a coordinate system without writing out ordered pairs. So instead of doing like 2, 4 to get an ordered pair, we do the point 2 plus 4i. Okay. Well, of course, this looks like some trigonometry to me. As soon as I see that, I picture in my head some triangles and angles, right? There's a distance from 2 plus 4i. Oop, boy, that's not very good. Not a very straight line right there. Let's get a line from 2 plus 4i down to the origin, and we can construct a right triangle. We've done this a lot, right, this semester? And so it's a triangle with one side of length 2, another side of length 4. Okay? Now, when we deal with real numbers and you take their absolute value, you're getting the distance from that real number to 0, right? An absolute value is defined as the distance between a number and 0. Well, we can do that with a complex number as well. So the absolute value of a complex number, or what we call the modulus of a complex number, is its distance from 0. Okay, so the distance from a complex number to 0 is along the hypotenuse of this right triangle. Okay, so you might say that the absolute value of 2 plus 4i, or what we call, again, the modulus of 2 plus 4i, is simply found using Pythagorean theorem. You have the square root of the sum of the squares, 2 squared plus 4 squared, which is, of course, here, let's see, that's 4 plus 16 is 20, square root of 20, and we simplify that. 20 is 4 times 5, so it's 2 times the square root of 5. Okay? So we can find an absolute value. That is the distance between a complex number and 0. It's also the length of the hypotenuse. Okay. Now the modulus we often call r, right? Kind of like for radius. It's the value r, so you'll see that as well. Okay, so because the a plus bi, the a gives you the sort of the x position or x direction, the b gives you sort of a y position or direction. Your textbook is actually going to start labeling these, instead of a plus bi, they'll call it x plus yi, which is okay. I'm going to go ahead and continue to use the a plus bi instead of the x and y. I just like that better because to me it shows the difference between what we're doing, but it doesn't really matter what notation you use. So when you are dealing with a complex number, and this is just a general one now in the first quadrant, but you know, we could put that in any quadrant, doesn't matter where it's at. And so you have the a value as one of the sides, the b value as the other one, and a plus bi as the point, r is the hypotenuse. Then all the relationships that we have for right triangles hold, right? The Pythagorean theorem, for instance, is a squared plus b squared equals r squared, right? Well, now I can just solve for r, so r is the square root of a squared plus b squared. Very simple. The a and the b come from the imaginary number, or I'm sorry, the complex number. We also have all of the trig functions in here, right? We have an angle theta. That's the angle between the positive x-axis and our complex number. And so the tangent of theta is equal to the b over a, which is the imaginary part divided by the real part. And we can also look at the sine and cosine. So with the sine, you have the sine of theta, which is opposite over hypotenuse, that's b over r. And of course, if you multiply both sides of that by r, you get b equals r times the sine of theta. Okay, that's going to be an important relationship. And also a similar idea for the cosine. Cosine theta is a over r, adjacent over hypotenuse. And if you multiply both sides by r, you would get a equals r times the cosine of theta. Okay? So this really gives us four very important formulas that help us to work with complex numbers now in trig form. So if we know of these four formulas, I'm going to set them off to the side here. So we have r equals the square root of a squared plus b squared. We have a equals r cos theta, b equals r sine theta, and tangent theta equals b over a. All right. So those are our four sort of foundational formulas here. Well, now, using those formulas, and again, your textbook likes to use x instead of a and y instead of b, but again, it doesn't really matter. For a complex number a plus bi, if you were to replace the a and the b with r cos theta and r sine theta respectively, you would have r cos theta plus r sine theta times I. Okay. Well, if you look at this, it's two terms now that have trig functions in them. We often factor the r out. There's a common r to both of these terms, and if we factor out the r, you get r times the cosine of theta plus, and now I'm going to write this so that the I comes before the sine, because it's a little bit weird to have the I following the sine that looks like it's in the angle. So I'm going to call that I sine theta. So it's r cos theta plus I sine theta. Okay? This is what we call the trig form of a complex number. You still have your real part, the r cos theta. You still have your imaginary part, which is the r sine theta, and your I is in there as well. Okay? But now we're using trig functions to define a complex number rather than just two real numbers. Okay, we also have a shorthand form of this. Some people would call this r times, let's do it this way. The cosine plus I sine is a very common expression in the study of complex numbers. And so to simplify that, instead of writing that out every time, we use an abbreviation called CIS theta. Cosine plus I sine. CIS. Cosine I sine. Okay? So you will see this occur if you see r times cis theta, I call it cis theta, but it's CIS theta. That really means it's cosine plus I sine, okay, of theta. Okay, so it's just a shorthand way of writing that. That's all that is. It's not really a new function or anything. Okay. So now we can convert between the two forms. We have our trig form, which could really be in either of these, the longhand or the shorthand. And then we have our rectangular or real form. Not real, yeah, I guess, whatever you want to call it, rectangular form. And so if I wanted to take the expression, or the complex number 2 plus 4i again, well, we already found the r value. The r value was square root of 20 or 2 root 5, okay? And so now we just need to find the theta. So theta, according to this bottom formula, is the inverse tangent of b over a. Well, that'd be 4 over 2, okay? The inverse tangent of 4 over 2, which is 2, so inverse tangent of 2 can be found using your calculator. That's not one of our nice values. About a 63.4 degree angle, roughly. Okay, now I do want to make sure we're in the proper quadrant, because remember the inverse tangent will only give you values that are in the fourth and first quadrants. And so this ends up in the first quadrant, as does this angle, as does the point. The quadrant of the angle given from the calculator should always match the quadrant of the point. If it doesn't, you need to correct that. So if my calculator gives me a first quadrant angle, but my point is actually in the third quadrant, I have to add 180 to it. Okay, so I just have to make the adjustment to get to the corresponding quadrant. Okay, so if I got 63.4 degrees, then my polar or trig form is going to be, I could write it in the longhand way, 2 root 5 times the cosine of 63.4 degrees plus I times the sine of 63.4 degrees. There you go, that's the long way to write it. Or we could do a shorthand way, which is just 2 root 5 CIS 63.4 degrees. Oops. Okay, and so you could really do either of these. Now, I'm not really sure. I believe my math lab is going to have you do the long form because your textbook puts their answers in this long form. So just be aware of that. Usually the textbook and my math lab are consistent, but the shorthand form is kind of nice. I just show it in case you need it for something. Okay, and then you can always convert the other way. So you could always convert from the trig or polar form to the rectangular form simply by multiplying 2 root 5 times this cosine, that gives you the A value, and 2 root 5 times the sine, that gives you the B value. Okay, we could even do an example. I'll pull a different one. So let's do something like, let's convert 3 times cosine of, let's do 225 degrees plus I sine of 225. We'll go with that one. Okay, so on this one, if I want to calculate this, what I need to do is, or if I want to convert this to the A plus BI form, all I need to do is calculate the cosine 225 and multiply by 3, calculate the sine of 225 and multiply by 3. Well, 225 is a 45-degree angle down here in the fifth quadrant. I said 5. In the third quadrant, right? It's a 45-degree angle down from 180. And so it's a third quadrant angle, so both of these should be negative. And we could calculate those, we could even do an exact form without the calculator because we know the special triangle, right? The 45, 45, 90 is 1, 1, and root 2. So the cosine of 225 is the same as cosine of 45 with a negative number on it, right? Or a negative on it. So that would be 1 over root 2, or simply root 2 over 2 if I rationalize that. Same with the I sine. The sine is also 1 over root 2, which is root 2 over 2. So this becomes I root 2 over 2. So both of those are root 2 over 2 because it's a 45-degree angle. Oh, but it's negative. I said it, but I didn't write it. Right? They should both be negative because they're in the third quadrant, right? The X and the Y are both negative. And then we distribute the 3 in, so we get negative 3 root 2 over 2 minus 3 root 2 over 2 times I. That would be the A plus BI form of that trig form. Okay, so now we can convert basically between the two very simply using these 4 formulas, and then just substituting the values, the angles or the radius or the A and B values wherever they need to go.